Take two coin-sized neodymium magnets, hold them a few inches apart, and let them go. They do not drift together gently. They slam together hard enough to pinch skin or even chip themselves. Now here is the strange part. To create that force, a factory melts the material, freezes it into thin flakes, crushes those flakes back into powder, presses the powder together, heats it again, and only near the end makes it magnetic. Why build the material just to break it apart again? Because making a powerful magnet is less about its shape than controlling what happens deep inside the material. For neodymium magnets, the factory starts with an alloy based mainly on neodymium, iron, and boron. Those ingredients are melted together in a controlled furnace until they become a uniform glowing liquid. Then comes the first reversal. Instead of casting one large block and simply machining it into shape, the molten alloy is cooled rapidly into thin, solid material. Fast cooling helps control the crystal structure that forms as the metal solidifies. That microscopic structure will later influence how well the material can be aligned and how strongly it can hold its magnetic state.
So the factory makes solid metal just to destroy it again?
Exactly. The first solid piece has the right chemistry, but not yet the internal structure the magnet needs. Turning it into powder gives the factory much more control over what happens next.
That powder stage is where the process stops looking like normal metalworking. The brittle alloy is ground into extremely small particles. Each particle contains crystal grains with preferred magnetic directions. The goal is to make millions of those tiny pieces cooperate before they are locked into one solid body. That control is one reason high-performance magnets can deliver so much force from such a small volume. Imagine a stadium full of people facing different directions. Now imagine everyone turning toward the same exit. The magnetic field used during pressing does something similar to the tiny grains inside the powder. The powder is placed into a mold, and a magnetic field helps orient the particles along the direction the finished magnet will eventually need. This is not yet the final magnetization. It is the preparation step that gives the material a preferred internal direction before the factory permanently locks the structure together. The pressed piece now has shape, but it is still fragile and contains tiny spaces between the particles. It has the form. Still not the finished magnet. So the compact goes into another furnace for sintering. Sintering heats the part enough for the particles to bond into a dense solid without simply turning the whole thing back into a pool of liquid. That matters because the factory wants a hard, solid part without wiping out the internal structure it just created. Heat treatment after sintering can further adjust the microscopic structure and magnetic properties. Now the part is hard, dense, and much closer to its final form. Still not the finished magnet. The sintered material can be ground or machined into discs, rings, blocks, arcs, and other shapes used in motors, speakers, sensors, and machines. Precision matters because the geometry and pole layout have to match the device around the magnet.
At this point, if I picked one up, would it already behave like the powerful magnet we know?
Not necessarily. It can have the right chemistry, the right structure, and the right shape, but the final magnetic state still comes later. That is the factory paradox. The part can be almost completely finished before it becomes the magnet the customer actually ordered.
That is the factory paradox. The part can be almost completely finished before it becomes the magnet the customer actually ordered. Before that final step, the surface may need protection. Sintered neodymium material is vulnerable to corrosion, so manufacturers often add a protective coating, such as nickel-based layers, zinc, or epoxy. The coating does not create magnetic strength. It protects the material underneath so the magnetic performance can survive real-world use. Now the part may look finished enough to ship. It can be shiny, precisely ground, coated, and dimensionally correct. Still not the finished magnet. Then the factory changes its behavior in an instant. The part is placed inside magnetizing equipment that produces an extremely strong magnetic field. Depending on the component, that field can come from powerful coils or specially shaped fixtures designed for a particular pole pattern. The pulse drives many magnetic domains into the final working arrangement. Once the external field disappears, the hard magnetic material retains a large part of that alignment. This is the moment the component becomes a working, permanent magnet. Everything before it was preparation.
So the fastest step is the one that finally gives the part the property we actually care about?
Exactly. The pulse may be brief, but it only works because the factory spent so much time preparing the material to respond correctly.
A stronger pulse cannot rescue poor chemistry, bad grain structure, weak alignment, or incorrect heat treatment. The final magnetization is dramatic, but the real quality was built into the part much earlier. That also explains why two magnets with almost identical dimensions can behave very differently. Their visible shape tells you very little about the grain structure, orientation, material grade, coating, or pole pattern inside. Engineers choose those details for the job the magnet must perform. A simple block may have poles through its thickness. A motor segment may need a different orientation. Some components need more complex pole patterns created by specially designed magnetizing fixtures. After magnetization, handling becomes more difficult. Before the pulse, the parts are easier to move around the factory. Afterward, strong magnets can jump toward steel tools or toward each other, with enough force to chip, crack, or pinch fingers. That matters because sintered neodymium magnets can be magnetically powerful while still being mechanically brittle.
That combination surprises people. Strong pull does not mean the material itself is tough.
So a magnet can be powerful enough to slam into a steel tool and brittle enough to damage itself.
To renew? Exactly. That is why handling, spacing, and packaging change once the parts are magnetized.
The finished magnets are then checked for dimensions, surface condition, magnetic strength, and correct pole orientation. For a motor or sensor, getting the pole direction wrong can make a perfectly strong magnet useless in the final assembly. Quality control therefore checks not only how much magnetic force the part can produce, but whether that force points where the design expects it to point. Only after those checks are the magnets ready to become parts of motors, speakers, sensors, actuators, and other machines. This factory process also explains why high-performance magnets look so simple from the outside. Almost all of the important work happened at a scale you cannot see. The factory controlled how the alloy cooled. It controlled how fine the powder became. It controlled how the particles were oriented. It controlled how the compact was sintered. It controlled the final dimensions, surface protection, and pole pattern. The result is not just a shaped piece of special metal. It is a material whose internal structure has been engineered for one specific magnetic job. That is what makes the process stranger than it first appears. The factory repeatedly melts, breaks, aligns, heats, cuts, and protects the material before the fastest step of all finally changes what the object can do. The final pulse is only the last command. The factory builds the structure. The pulse makes it magnetic.